Hello, and welcome to Mr. Ambrose's video on the alternating series estimation theorem. This will be one of two videos on topics that we were not able to cover in class, but that you could potentially see on the actual AP exam. Before I start discussing this particular theorem and how it works, I'd like to review two major themes of the series unit that we covered in class. One of the themes was in trying to construct series to represent functions. An example of this you see on the screen because that series we have there is the Maclaurin series for our cosine function. The second major focus that we looked at in series was trying to determine when a series converged and identifying all the different tests we have to actually accomplish that. The goal of that was to ultimately be able to determine the interval of convergence of a particular power series on a function. And that, in layman terms, basically meant for the equation that we see on the screen there, for what x values is the cosine function equal to that Maclaurin series. That's what the interval convergence tells us. Now, those two particular tools are helpful to perhaps evaluating functions like cosine and sine or e to the x, which are difficult to evaluate without the aid of a calculator. But there's still a fundamental problem with trying to add up an infinite number of terms. Unless your series is geometric, this is very, very difficult to do. So the alternating series estimation theorem, it allows us to work with partial sums, which we very well can calculate, and use those partial sums to determine how close we are to the actual sum of a particular series, even though we might not know what that actual sum is. So to show you how this works, I would like to work with the cosine Maclaurin series, and in particular, I'm going to use that to try to approximate what is the cosine of 1 by looking at partial sums of this particular Maclaurin series. Now, one of the conditions to applying this particular theorem is that we need an alternating series, and hopefully you would agree that the Maclaurin series for cosine is an alternating series. So what I'm going to do now is I'm going to calculate a few of these partial sums. So the first partial sum I'd like to do is the sum of the first two terms of the particular series. And what I'm going to do for that is I'm going to take this x equals to 1 and plug that in over here to get the sum of the first two terms of the Maclaurin series with the cosine of 1. And that would just be 1 minus 1 squared, which is 1, over 2 factorial, which is 2, and 1 minus a half is just 0.5. So now I'm going to move on to the next partial sum and sum up the first three terms to our particular series. And that would be taking 1 and plugging that in to the first three terms of a Maclaurin series for cosine. And that would be 1 minus 1 half plus 1 to the fourth power, which is 1, over 4 factorial. And if we add up these three terms, we get a value of 0.541, and then we're going to get a repeating decimal 6. Now, I should say these calculations I'm doing somewhat fast, but if you want to check them out on your calculator, by all means, please do so. Now I'm just going to move on to the last partial sum, which will be the sum of the first four terms of our particular series. And for that, we would have to add on the next term of our particular series by plugging 1 into our Maclaurin series for cosine. And that would be 1 to the 6th power, which is 1, over 6 factorial. And that is equal to 0.54027, and then we're going to get repeating decimals. All right. Now these are partial sums. The sum of the first two terms, sum of the first three terms, sum of the first four terms. What I'm going to do next is I'm going to compare these partial sums to an actual calculated value for the cosine of 1. And if you want to verify this on one of your own calculators, you can. But the cosine of 1 is this 0.5403023, so on. And so I will perhaps just write that up on top here. That, again, cosine of 1 is 0.540 3023. And what I'm going to do now is I'm going to calculate the difference between this value, which is, we know, is the correct value for the cosine of 1 out to 7 decimal places, and take the difference between that value and these partial sums. So when we take the difference between that and the first partial sum, we get a difference of 0.0403023. Now, you may say, okay, I have a calculator, why do I need to do this particular calculation? But the significant part of this difference is that if we were to continue to calculate values of our cosine Maclaurin series, the next term of the series would be when we plug 1 into this third term, and we would get a value of 1 over 4 factorial. That's the first term that is not included in this partial sum if we were to continue moving on. And the interesting thing about 1 over 4 factorial is that it is equal to 0.041, and then we're going to get repeating decimals of 6. And when we compare this first excluded term to the actual difference, we see that this term here is more than the actual difference between the second partial sum and the actual sum of the series to the first 7 decimal places. And so that's an interesting fact. And if we continue to do this with our other partial sums, we start to see a pattern. For example, again, our third partial sum was this value of 0.541666, and if we take the difference between that and the actual value for the cosine of 1, we get a value of 0.001364. And if we then consider the first term that's not included in this partial sum, which is this going to be this 1 over 6 factorial, well, 1 over 6 factorial, if we calculate that, that is equal to 0.00138, and then we're going to get repeating decimals here, I believe. And once again, this particular value, the first excluded term, is greater than the actual difference between the cosine of 1 and this partial sum. And to highlight this, that this continues to work, if we look at our fourth partial sum, the difference between that sum and the actual value for cosine of 1, we get a value of 0.00024, and then I think because of rounding, this may be slightly off, but I believe it's 5 if you properly round. That difference is going to be less than the value of the first excluded term to this particular partial sum. And if we were to continue adding terms of our Maclaurin series, the next term, hopefully you would agree, is 1 over 8 factorial. And 1 over 8 factorial is equal to 0.0000248. And so we get this particular process where if we add up a particular sum of terms in an alternating series, that particular sum, if we the difference between the actual sum and the partial sum of the series and the actual sum of the series, that difference will be no greater than the first excluded term. And so this is basically what the alternating series estimation theorem basically says. First, again, you need an alternating series, and you need it to know that it converges. The basic idea is that the error of any partial sum is no greater than the first excluded term of the partial sum. And so what that basically means is that if we look at the difference between the actual sum and the partial sum, that difference, which some people will refer to as the absolute error, but that difference can be no greater than the first excluded term to that particular partial sum. It really is, if you understand this particular concept, is not that difficult of a theorem to apply, but usually it does cause some difficulties for students. Now, to further hopefully reinforce why this works, I'm going to refer you back to when we proved the alternating series estimation theorem and kind of show you, well, how does this in particular work? So let's consider, again, a particular alternating series whose sum is located here on our number line. And if you recall, again, we have an alternating series here. We start off with the first term being positive, so the first term's value is this length here, and the first partial sum is located here on the number line. And then because the series is alternating, the next particular term, for some slight technical difficulties, but getting back to this rudimentary proof of the alternating series estimation theorem, again, first term of the series is positive, first partial sum is located here on the number line. Second term of the alternating series is negative. The value of that second term is represented by that line segment, so the partial sum value is located here for the second partial sum. And if you recall, this process continued to happen because the terms of the series in absolute value have to be decreasing and decreasing down to 0. So if we say, let's consider we do, again, our fourth partial sum. The fourth partial sum value is located right over here on the number line. And the actual sum of the series, which, again, in most cases you're not even going to know what it is located right over here. So what this theorem basically says is that the difference between these two values, which is really going to be represented by this distance, that value is no greater than the first excluded term to this fourth partial sum. And the first excluded term to the fourth partial sum would be represented by this line segment of b sub 5. And it's clear to see here that this particular value is greater than the difference between the fourth partial sum and the actual sum of the series. And if you look at this for any particular partial sum of your series in an alternating series, you see that this continues to happen. So for example, if we consider the third partial sum, the difference between the sum and the third partial sum is represented by perhaps this line segment here. And this is no greater than the first excluded term from the third partial sum. And that first excluded term would be the fourth term of our alternating series, which would be this b sub 4 here. And once again, it's clear to see that this value is greater than the difference between the sum and the partial sum of our series. So that's the basic gist of the alternating series estimation theorem. We will definitely see this in review. I will try to make sure that we look at problems where this would be applied. It's not common, but you could potentially see it, and hopefully this will help you answer that particular question if you do see it on the AP exam. Well, I hope that this video was helpful to you, and I hope that you get to enjoy the rest of your vacation. Take care.